Good day, my name is Dinesh Naidu from DDT2B, and today my groupmates and I will be presenting our case study 1. This case study is about minimal spanning tree and what is the importance of it, and also the techniques in minimal spanning tree. Next, take a look. Now the group members are yours truly, Dinesh Naidu, and that is my student ID. Next, who will be presenting is Hua Junwei, and then Tam Chi Yu, and so on, Maria Farhana. Now, to introduce minimal spanning tree, first of all, we must know what is spanning tree. A spanning tree, our graph with a number of vertices, is a subset of edges. And how do we find the edges? You just subtract 1 from the number of vertices. And that number of edges form a tree. For an example, as you can see here, graph G has 3 vertices and it also has 3 edges. Now, to make a spanning tree, we take the number of vertices, we minus by 1, and then we connect those two, those two, those 3 vertices in with the number of edges, with the number of vertices minus 1, and that gets you the number of edges. As you can see here, this graph, this is the normal graph, has 3 vertices, and in the spanning tree, there is still 3 vertices, but there is only 2 edges, meaning this is a spanning tree of a graph. So, any point can become a parent as long as it doesn't form a loop. A graph can have a spanning tree as long as it doesn't form a loop. So as you can see here, this will connect, A will connect to B and will connect to C. As this goes, it can be either B or C. C connects to A connects to B. All 3 vertices are connected through a spanning tree. Now, what is a minimal spanning tree? A minimal spanning tree is the spanning tree where the cost is minimum among all the spanning trees. What does the cost mean? The cost of a spanning tree is the sum of the weights of all the edges in the tree. And what are weights? Is how heavy or how what is the, let's say, value of the edges. You can say length, you can say weight, but mainly it's called the sum of weights. So the cost of the spanning tree is the sum of the weights. So as you can see here, for the normal graph tree, the sum of weights is 6. But in a minimal spanning graph, we find the minimum cost among all the spanning trees. So how do we find the minimum? We use minimum spanning tree technique, which shall be explained in the slide by Tam Chiu, in the next slide by Tam Chiu.
Hi, my name is Tam Chiu and today I would like to talk about technique applied to find the minimal spanning tree for a graph. There are two methods to find the minimal spanning tree for a graph. First, prime algorithm. The tree that we are making or growing always remains connected and grows a solution from a random vertex by adding the next smallest vertex to the existing tree. Next, prime algorithm is also used faster for dense graph. Dense graph is number of edges which is close to number of vertices power 2. Next, Kruskal algorithm. The tree that we are making or growing usually remains disconnected. Next, Kruskal algorithm also grows a solution from the smallest edge by adding the next smallest edge to the existing tree. And Kruskal algorithm is faster for sparse graphs. Sparse graph is number of edges is close to the number of vertex. That's all from me.
Hi guys, my
Question
name is
2.
Quazurev and my card entry number is 01 DDT20F 1058. Today, I am going to show B. Question number 1. The question number 1, I am using Costa algorithm. The Costa algorithm is find the edge in the graph with smaller wedge. If length is more than 1, pick one at the names. Please marking with red color for the edge. So the question number 1, I use Costa algorithm. The Costa algorithm is smallest wedges. The smaller wedges in the question number 1 is 1 kilometer at the apical to Maria. So we can marking. So the second is 1.1 not got in the question number 1 the graph. So we go to 1.2. The 1.2 got 2. The number 1 is Mikata to Nanima. The second is Nanima to Habishi. So we can marking. Okay, 1.2 run. So the 1.3 got in the graph. Okay, 1.3 at the Tahikawa to Maria. So we can write. Okay, in the graph, no got 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, 2.0 got. So we want just the 2.0 at the Nona to Haruma. So we can write. Okay, see the question number 1, the graph. No got 2.1 and 2.2. Okay, go to 2.3. Good. Okay, 2.3 also got 2. The number 1 is Nanima to Nona. The number 2 is Haruma to Yokohama. So we can choose the two in the graph. So we can write. Okay, the 2.4 got the graph question number 1. So the 2.4 from Habashi to Amico. So we can write. Okay, the 2.5 got, but we cannot use because the use the 2.5. Okay, the graph got looping, so we cannot use. Okay, the 2.6 not got, 2.7 not got, 2.8 not got, 2.9 not got, 3.0 not got, 3.1 not got, 3.2 not got. So we use the 3.3. The 3.3 got at, from the Yamato to Roma. So we can write. So finish this answer for question number 1. Okay, we all the draw new diagram for question number 1. We go to the calculation for question number 1. The number 1 is M to N 1.2 kilometer. The number 2 M to H 1.2 kilometer. Number 3 is N to N 2.3 kilometers. Number 4 is Y to N 3.3 kilometer. The number 5 is N to H 2 kilometer. The number 6 is H to Y 2.3 kilometers. And number 7 is T to M 1.3 kilometer. The number 8 is A to M 1.1 kilometer. The number 9 is H to A 2.4 kilometer. And total wages is 17 km. And thank you.
Question 2. I'll be using Kruskal algorithm to find the minimal spanning tree for this graph. Welcome to Seoul. First, we will find the smallest edge in this graph, which is Bucheon to Guri 0.5 km. So we highlight it, and next we will find the next smallest edge in this graph, which is Anyang to Songnam 0.9 km. Next, the next smallest edge in this graph is Songnam to Gwangmyeong 1.0 km. And next smallest edge is Guri to Sihyong and Guri to Songnam 1.2 km. Same, so we will highlight both. Guri to Sihyong and Guri to Songnam. And next, we'll find the next smallest edge in this graph, which is Buchon to Goyang, 1.4 km, so we highlight it. And next, smallest edge in this graph is Guri to Hanam and Gwangmyeong to Hanam, 1.5 km. But we can do both. If we do both, it will create a loop. So I will choose one, which is Guri to Hanam, 1.5 km. Next smallest edge is Anyang to Icheon, 1.8 km. So we highlight it. And next smallest edge in the graph is Songnam to Incheon, 1.9 km, and Bucheon to Anyang, 1.9 km also. But if we highlight this Bucheon to Anyang 1.9 km, it will create a loop. So we can't highlight it. And Songnam to Incheon also the same, which will create a loop. And so we'll find the next smallest edge in the graph, which is Hanam to Namyangju, which is 2.0 km. So we will highlight it. And now we are done. So we need to check first if all the vertices is connected. So Goyang to Bucheon, Bucheon to Guri, Sihyong to Guri, Guri to Hanam, Guri to Seongnam, Anyang to Seongnam, Anyang to Icheon, Seongnam to Gwangmyeong, Guri to Hanam, and Namyangju to Hanam. Okay, all the vertices are connected. So we are done. And next, for the next step, to find the minimum spanning tree using Kruskal algorithm, we will total up the weight of the graph that has been highlighted in the previous slide. And we will total all the weight of all the edges, and we will get 11.5 kilometer, which is the minimum spanning tree of this graph. Welcome to Seoul. Okay, that's all from me. Thank you.
For the number 3, I am using Costa algorithm. Costa algorithm is smaller wedges. You can see question number 3 graph. The small range is 0.5. So we P to SS. So the wedges is 0.5. So we can write the 0.5. We find the 0.6 not got, 0.7 not got, 0.8 not got. So 0.9 got in the DM to CP. So we can write. So 0.9 km run already. We got to find 1 kilometer, 1 km. Got 2. one in the VM to P. The second is NAH to DM. So we can write the two. Okay, we run 1 kilometer. So we got to find 1.1. 1.1 also got 2. NAH and CP. So you cannot use this because the here got looping. So we find the 1.1 under got DM to C. So we can use the DM to C only 1.1. Okay, we run 1.1 kilometer. We go to find 1.2 kilometer. The 1.2 kilometer got 2 pages. The one pages is CP to P. Okay, the second is N to MM to DM. So got 2. We can write the 2 function the edges. We all run 1.2 kilometer. So we go to find the 1.2 kilometer. The 1.3 got, but we now can use, okay, because the NM to C got looping, so we can use this. So we go to find the 1.4 no got, 1.5 no got, 9.6 no got, not 1.7 no got, 1.8 no got, 1.9 got. Okay, from C to MB, so we can use. Okay, we all finished 1.9 kilometer. Go to find the 2 kilometer. 2 kilometer got 2. The number 1 is VM to CP. CP got looping, so we can use this 2 kilometer. We go to find the SS to LP. Okay, LP no got looping, so we can use. So use. Finish this question 3 for the answer. Okay, we finish draw the new diagram. We go to the calculation for the question number 3. The number 1 is NAH to DM 1 kilometer. The number 2 is MN to DM 1.2 kilometer. The number 3 is DM to C 1.1 kilometer. The number 4 is C to MB 1.9 kilometer. The number 5 is DM to CP 0.9 kilometer. The number 6 is CP to P 1.2 kilometer. The number 7 is P to VM 1 kilometer. And the number 8 is P to SS 0.5 kilometer. And the last one is SS to LP 2 kilometer. Okay, the total wages is 10.8 kilometer.
Olympic Park to Yarra Park 1.0 km, Yarra Park to Royal Botanical Gardens 1.4 km, Olympic Park to City Centre 1.2 km, City Centre to Flagstaff Gardens 1.5 km, Flagstaff Gardens to King's Domain 1.8 km, King's Domain to Royal Exhibition Buildings 1.6 km, Royal Exhibition Buildings to Fitzroy Gardens 1.7 km, Royal Exhibition Buildings to Melbourne Museum 2.2 km, Melbourne Museum to Government House 2.2 km, and then total addition to all weekdays and total week 4.6 km.
Right
Conclusion.
now we're
What
gonna
is the
do Welcome to Police by me, Dinesh Arajanaidu. And first step is to see which algorithm we're going to use. Right now I'm going to use Prim's algorithm to solve this. And yeah, the first step to Prim's algorithm is to find the vertex that is connected to the edge with the least amount of weight. And as you can see here, this edge is connected to two vertices, and you can choose either one of these vertex, but I choose Pearly State Park as my vertex starting point. So let's start. So let's connect these two vertices as it is connected by the edge with the smallest weight. So let's do that. Next, the second let's find another vertex that is connected to the smallest weight. It can be smaller than this weight, or it can be slightly larger but smaller than all the other weights. So as you can see here, this vertex can connect to city center, Harumani stall, which is shorter, 1.2. But there's also this vertex, but it is connected to Malati Lake and Tima Taso Lake and city center. But as you can see here, this is the smallest among them. So we're just gonna choose this one, Royal Gallery to city center. Next, we choose the next with next edge is connected to a vertex with the smallest amount of weight. So as you can see, if you compare all of these, this can be Royal Gallery can go to Harumani stall, City Center can go to Harumani stall, but these are too big. I feel like these are too big. You can find smaller. City Center, Homestay, still too big. City Center on Lati Lake, yes, that's the right amount. And City Center to Tima Taso Lake, but as you can see here, Pearly State Park to Tima Taso Lake is the shortest among all the others, as it is 1.4 while the others are already more than 2. And the next one, as I shown before, 1.5 kilometers, city center to Malati Lake. Then we see the shortest one that is connected. So let's find the shortest one. City center to Harumani Stall, Pearly State Park to city center. Why we cannot choose this? Because this will form a loop, and in a tree a loop cannot be formed. So let's see, Tima Taso Lake, no. 3.9, 6.0, no, I would rather not. So let's find the shortest one, shall we? So 2.5 is the shortest among I've seen, and yes, right here. So let's see. Yes, this is the next edge to connect Harumani stall. And next we're gonna find another edge with a small amount of weight, the smallest among the others. So as you can see here, 2.4, yes, it is the smallest, but it will form a loop. Let's find this. Let's find the next one, shall we? Okay, the next one, if you look at all these, 4.8, 5.4, no, cannot, so too big. 3.9, still too big. We cannot choose this as it is still a big number and it forms a loop. This is actually optional because it connects a new vertices that is not included. But as you can see here, the shorter part is city center to homestay. So let's take this part. Next, the shortest part is actually this one, but since it will connect these two vertices together, it will form a loop, and we cannot have that. So next, we're gonna find the shortest one. Yes, this is also a short edge with a small weight, but as you can see, it will form a loop if we connect it, and trees cannot have a loop. So the only one that doesn't have a loop, it is the shortest among them, is this one, Homestay to Kuala Sanglang. But as you can see here, Malati Lake to Sugarcane Plantation cannot, as a 5.4, and Melati Lake to Padang Besar is 4.8, and Timor Taso Lake to Padang Besar is 6.0. Among all of them, this is the shortest. Let's take this one. Next, let's find the shortest one again. Still, 5.4 is still too long, but as you can see here, there's a 3.7 weight right here. So we'll take Kuala Sanglang to Sugarcane Plantation. Then the shortest one, as you can see here, is 2.6. Among the others, is way too big. And as you can see, the graph is complete as there are no more vertices to be connected. All has been selected. So now we're going to find the total weight. This is after all a minimal spanning tree, so we're gonna find the total weight. So as you can see here, Yes, there is 9 edges in total, and there is 10. And if you want to check if your spanning tree is correct, just count how many vertices you have. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And how many edges do you have? 9 edges. So that means your spanning tree was a success, as there is 10 vertices and 9 edges, and a spanning tree's formula to find n amount of vertices and to find the number of edges is n minus 1. So this is correct. Now we need to find the total weight, the cost, the total distance traveled. This is the minimal amount, so that's fine. The total weight is 21.1. So this is the minimal amount of distance that needs to be traveled between all these points. Let's go. Thank you.
Conclusion. What is the importance of minimal spanning tree? Minimal spanning trees are used for network design such as telephone or cable networks, as to find approximate solution for complex mathematical problems like the traveling salesman problem. Circuit design implement efficient multiple constant multiplications.